Hi students, welcome to the section of normed linear space capital LP. In previous sections, actually we defined the spaces L1 of E, which is equal to set of all measurable functions, right? Measurable functions on E such that integral over E mod F is finite, where E is a measurable set, where E is measurable subset of real line, okay, and F is a measurable function, measurable real valued function. So the L1 of E is nothing but set of all integrable functions, Lebesgue integrable functions defined on a measurable set E. And we have proved that L1 of E is a normed linear space under the norm 1 norm. 1 norm is defined by 1 norm of F is equal to integral over E mod F. Okay. Therefore, the capital LP, the space capital LP of E, where P equal to 1 is a normed linear space. We already proved in this previous section. And what about this is true for P equal to 1, okay? And for P equal to infinity, we have L infinity of E. What is L infinity of E? Set of measurable functions which are essentially bounded on E. Okay? So that means this is equal to set of all functions f such that mod f of x is less than or equal to m almost everywhere on E, where m is called the essential supremum or essential bound of f. Okay. And we proved that this L infinity is also normed linear space under the norm essential subnorm, that is denoted by infinity norm f is equal to essential supremum of f. Okay. Now we are going to prove that this capital LP for 1 less than P less than infinity. For all other cases in between 1 and infinity, LP is we are going to prove LP of E is a normed linear space. So how will you prove that this space is normed linear for 1 less than P less than infinity? For P equal to 1 and P equal to infinity, we already proved in the previous sections. Okay. So we have to verify all three axioms of normed linear space, which are non-negativity, positive homogeneity, and triangle inequality. First, we consider what is non-negativity condition for this space. So I consider F belongs to LP of E. Okay. Then I define norm which is denoted by P norm. Okay. For the case it is 1 norm. For the case it is the subnorm, infinity norm. For the case P, I denote it is P norm. P norm of F is equal to integral over E mod F raised to P. Okay. Then under this norm or this norm P norm satisfies all the conditions of normed linear space. Okay. So for that F belongs to LP of E means integral over E mod F raised to P is finite. That means integral over E mod F raised to P exists. It is finite. So whatever that value is denoted by corresponding P norm of F. Okay. Then it is a clearly real valued function. Then I need to verify the non-negativity condition. What is P norm of F? Is it positive or negative? We know mod F will be always positive, right? Then mod F raised to P will be a positive number. Then integral over E mod F raised to P will be again positive, right? So this is equal to integral over E mod F raised to P, which is always positive. Therefore, P norm of F is always greater or equal to 0 for every F in the LP of E, since mod F is positive. Okay. So what happened if P norm of F equal to 0? When P norm of F equal to 0, integral over E mod F raised to P equal to 0. So Lebesgue integral of a function is equal to 0 means that function is equal to 0 almost everywhere on E. In mod F raised to P equal to 0 almost everywhere on E means mod F equal to 0 almost everywhere on E. So mod F equal to 0 almost everywhere on E if and only if F is equal to 0 almost everywhere on E. So using that idea we get mod F P norm of F equal to 0 implies F equal to 0 and F equal to 0 implies P norm of F equal to 0. So non-negativity condition will be true. Next, for the homogeneity, positive homogeneity, I take alpha is a real number and f is an element in LP of E. Okay. Now, you consider p norm of alpha f. By definition, it is integral over E mod alpha raised to p. Right. So, which can be written mod alpha raised to p can be taken outside integral over E mod f raised to p. That is mod alpha raised to p can be taken out integral over E norm f raised to p is nothing but what is that? P norm of f. P norm of f. Okay. I'm sorry, P norm of f is actually defined by this raised to 1 by p. Okay. This is actually raised to p. There is a mistake. It is 1 by p. Okay. Sorry. And this is raised to 1 by p. Whenever f is positive, its 1 by the power will be also positive. Okay. So this will happen raised to 1 by p will equal to 0. 1 raised to 1 by p 0 means that integral equal to 0. Then all of these will become similar. Okay. So this raised to 1 by p and this raised to 1 by p. Okay. So mod alpha raised to p whole raised to 1 by p and p norm of f. So mod alpha raised to p whole raised to 1 by p is mod alpha into p norm of f. Ready? Okay. So we get p norm of alpha f is equal to mod alpha into p norm of alpha. So we get the positive homogeneity. Now we need to prove the triangle inequality. Please don't forget p norm of f is equal to integral over E mod f raised to p whole raised to 1 by p, that is whole raised to 1 by p. And this is the definition of p norm. Now for the triangle inequality, actually we want p norm of f plus g, right? P norm of f plus g is less than or equal to, we want for the triangle inequality p norm of f plus g is less than or equal to p norm of f plus p norm of g. This is we need to prove for the last third axiom of normed linear space. But we can't prove this statement directly. To prove this, we want to verify some more axioms or some more lemmas which are helpful for proving this inequality. Okay, so for that I would like to define, actually this is a pending one. Okay, if you can prove this statement, then only we can say that capital LP of A is a normed linear space. So this inequality is actually called Minkowski's inequality. Minkowski's inequality. So this will be proved later. So before that I am going to prove that what is Young's inequality. Now I am going to define what is a conjugate of a number. Suppose p is a number belongs to open interval 1 comma infinity. Okay, 1 less than p less than infinity. Okay. Then the unique number q such that if you consider 1 by p plus 1 by q equal to 1, that unique number corresponding to this p is called conjugate of p. Then q is called conjugate of p. So you can solve that when 1 by p plus 1 by q equal to 1, which implies actually q will be equal to p by p minus 1. Okay, so when p belongs to 1 comma infinity, then q equal to p divided by p minus 1, and this number q is called conjugate of p. And p can be, we can say p will be conjugate of q. Okay, then we go to Young's inequality. Young's inequality. So for a 1 less than p less than infinity, q is the conjugate of p, that means 1 by p plus 1 by q equal to 1, and any two positive numbers a and b, we need to prove that ab is less than or equal to a raised to p by p plus p raised to q by q. This inequality is called Young's inequality. So how will we prove this statement? So for that I am going to define a function g such that g of x is equal to 1 by p into x raised to p plus 1 by q minus x, where x is greater than 0. For a positive real number x, I define g of x equal to 1 by p into x raised to p plus 1 by q minus x. Okay. Then what will be g dash of x? G dash of x is equal to 1 by p into x raised to p minus 1 plus 0 minus 1, and that will be x raised to p minus 1 minus 1. Okay. Then when x belongs to the interval 1 comma infinity, that means which is greater than 1, when x is greater than 1, then what will happen? G dash will be positive. Okay. When x belongs to the interval 0 comma 1, because x can take on only positive values, right? X is defined, function is defined for positive real numbers. So I split this number into hold the positive real line into two subintervals, 0 to 1 and 1 to infinity. Okay, because 1 is a critical point for this function, right? So I can say that g dash will be positive for x belongs to 1 infinity, and when x belongs to 0 to 1, g dash will be negative. Since x equal to 1 is a critical point, or g dash of x is equal to 0 implies I can say x equal to 1. Okay. And also for x greater than or equal to x greater than 0, we have g is a function. Since x is greater than 0, g of x is also greater than 0, right? Greater than or equal to 0. So which implies 1 by p into x raised to p plus 1 by q minus x will be greater than or equal to 0. So I can write x will be less than or equal to 1 by p into, so x less than or equal to 1 by p into x raised to p plus 1 by q. So that means since x is positive, x will be less than or equal to, by the property of g, we can write 1 by p into x raised to p plus 1 by q. Okay. Now that means there will exist a point which will be less than or equal to this number. So I take x naught satisfies this condition. So let x naught is less than or equal to some 1 by p x naught raised to p plus 1 by q. അതായത് ഇത് സാറ്റിസ്ഫൈ ചെയ്യുന്ന ഒരു പോയിന്റ് അവിടെ ഉണ്ടാവുന്നല്ലേ അതിൻ്റെ അർത്ഥം. അപ്പോൾ അങ്ങനെ ഒരു പോയിന്റിനെ ഞാൻ എക്സ് നോട്ട് ആയിട്ട് വിളിച്ചു. ഓക്കെ. സോ എക്സ് നോട്ട്, there will exist a point x naught says that x naught will be less than or equal to this number. Okay. If we take x naught is equal to, if x naught is equal to some a by b raised to q minus 1, then what will happen? A by b raised to q minus 1 will be less than or equal to 1 by p into a by b raised to q minus 1 raised to p plus 1 by q, right? Or this can be solved. So that means a by b raised to q minus 1 less than or equal to 1 by p a raised to p divided by b raised to q minus 1 into p plus 1 by q. So what is q minus 1 into p? We have 1 by p plus 1 by q equal to 1 because q is a conjugate of p, right? So we have q will be of the form p equal to p minus 1, or q into p minus 1 will be p. Similarly, I can write what I can write p plus q equal to pq, right? By cross multiplication this statement, p plus q will be equal to pq, and p minus, or I can write pq, right? pq minus p will be equal to q. Okay, pq minus p will be equal to q. Then p into q minus 1 will be is equal to q, right? So p into q minus 1 will be equal to q. So in here p into q minus 1 can be taken as q. So this will be a divided by b raised to q minus 1 less than or equal to 1 by p. I take a raised to p divided by 1 by p into 1 by b raised to q plus 1 by q. Now I multiply this whole inequality by b raised to q. So what will happen? A b raised to q, if you multiply by b raised to q, this will be cancelled and you get a into b, that will be less than or equal to b raised to q, b raised to q will be cancelled, a raised to p by p plus b raised to q by q. So this is Young's inequality. Okay. Okay, now we move to the next theorem. Theorem says that let A be a measurable set for 1 less than or equal to p less than infinity and q be the conjugate of p. If f belongs to Lp of E and g belongs to Lq of E, then their product f into g is integrable over E and the Holder's inequality is satisfied. What is the Holder's inequality? Which is integral over E modulus of f into g will be less than or equal to p norm of f into q norm of g. Moreover, if f is non-zero, then we can define a function f star, that f star is equal to p norm of f raised to 1 minus p into signum of sgn, means signum of function of f, into mod f raised to p minus 1. Then this function f star belongs to LQ and integral over E f into f star equal to p norm of f. And you can prove that q norm of f star is equal to 1. Okay. And when this kind of function exists, this function is called actually conjugate of f star is called a conjugate of f. I can write here f star is called a conjugate of f. Conjugate of the function f. Okay. So please remember the Holder's inequality, integral over E mod f into g will be less than or equal to p norm of f into q norm of g. And this Holder's inequality is proved for proving Minkowski's inequality. What is Minkowski's inequality? It is nothing but the triangle inequality of the space capital LP of E. Okay. So we will prove this theorem. So we will prove this theorem by case 1. Case 1, p equal to 1. We need to prove that 1 less than or equal to p less than infinity. We divide this case into p equal to 1 and p belongs to 1 less than p less than infinity. Okay. For the case p equal to 1, when we take p equal to 1, what will be the conjugate of p? Then conjugate of p, that is q equal to, q will be infinity, right? Q will be infinity. Because 1 by p plus 1 by q must be equal to 1. So when p equal to 1, this is 1. 1 plus something equal to 1 means 1 plus 1 by infinity will be goes to 0. So 1 by infinity will goes to 0 means q will be infinity, right? Then only we get 1 by plus 1 by q equal to 1. Okay. So when p equal to 1, q will be infinity, right? So for the case p equal to 1, we need to verify this condition when f belongs to LP of E. So let f belongs to LP of E. LP of E means actually L1 of V because p equal to 1. And G belongs to LQ of E. LQ of E means that is G belongs to Q here infinity, so L infinity of E. Then we need to prove f into G is integrable and it satisfies this inequality. What is f into G? Is it integrable? F into G. Since f belongs to LP, f belongs to L1 of E. L1 of E means mod f is integrable, right? I can write here, since f belongs to L1 of E implies integral over E mod f is finite. Is finite means is exist. Okay. And since G belongs to L infinity of E, what it means? G is essentially bounded. Essentially bounded, its essential supremum will exist. Okay. Then what is their product? Is it integrable? F into G. Since mod f is integrable implies f is integrable. When mod f is integrable, f will be integrable. And G is an essentially bounded function. So that means it will be also integrable, right? So their product f into G will be integrable over E. Okay. Now we will verify this inequality for the case p equal to 1. So for p equal to 1, we want to verify the Holder's inequality. So for p equal to 1, what will be that? Integral over E mod f into G will be less than or equal to actually p norm of f into q norm of G, right? So for p equal to 1, what will be this? Integral over E mod f G is less than or equal to 1 norm of f into q norm means will be infinity, right? Subnorm, essential subnorm of G. This is we need to verify. Okay. So I consider this is our claim, okay. I consider integral over E mod fg. This can be written integral over g mod f into mod g, okay. So for any function, what will be mod g? Since g is an element in LQ means here L infinity of E, g is essentially bounded, right? G is essentially bounded. Then g has essential supremum, right? Essential supremum of g exists. Okay. What is essential supremum? Whenever mod g of x is less than or equal to m, infimum of that m's are called essential supremum. Okay, then we can write modulus of g of x will be less than or equal to m, where this m can be taken as essential supremum, right? Essential supremum of g. Okay, so always modulus of g of x will be less than or equal to essential supremum of g. So instead of mod g, I can write this will be less than or equal to integral over e mod f into, instead of mod g, I can write essential supremum of g. Okay. So essential supremum of g can be taken outside from this integral. So that will be equal to essential supremum of g into integral over e mod f. So this is equal to, what is this essential supremum of g? Essential supremum of g is nothing but infinity norm of g, right? What is this integral over e mod f? Integral over e mod f is nothing but 1 norm of f by definition. So you get integral over g mod f g equal to 1 norm of f into subnorm of g. So we proved this inequality. So which implies integral over e mod f g is less than or equal to 1 norm of f into subnorm of g. For the case of p equal to 1, we proved the Holder's inequality. This is okay. Okay, now we need to prove that if f is non-zero, comma, the function f star equal to, we define p norm of f into 1 minus raised to 1 minus p into signum of function f into mod f raised to p minus 1, okay, comma, f star is equal to, if we define f star is equal to this, we need to prove that this function f star belongs to LQ. Okay, we have to prove that this function f star belongs to LQ. Here LQ of E is LQ is nothing but L infinity. That is, we need to prove f star belongs to L infinity. Okay, L infinity. So how will we prove this function f star belongs to L infinity? We need to prove that f star is essentially bounded function. So what is it essentially bounded? So for that we need an essential bound for this function f star. So what is modulus of f star? Modulus of f star is equal to modulus of this whole thing, p norm of f raised to 1 minus p, signum of function f, signum of f into mod f raised to p minus 1. So p norm of f raised to 1 minus p is a number. P norm of f will be a real number. Therefore, that real number raised to 1 minus p is again a real number. So that can be taken outside. Okay, and mod f raised to p minus 1 again a number, so that raised to p minus 1 can be taken outside. Then inside of modulus there is a function signum of f. What is signum of f? Signum of f is a function which is defined by, it has only two values, either 1 or minus 1. It is 1 when f of x is positive greater than or equal to 0. It is minus 1 when f of x is negative. So this is the definition of signum of function. And what is modulus of signum of function? Modulus will be always 1, right? Mod 1 or mod minus 1, that all are 1. So modulus of signum of function is nothing but 1. So I can write this will be equal to mod f raised to, p norm raised to 1 minus p into mod f raised to p minus 1, because this will be equal to 1. This thing goes to 1. Okay. So this will be a well-defined number. This well-defined number can be taken as the essential bound for f star. So f star will be essentially bounded function, which implies f star is essentially bounded. Essentially bounded. What is the essential bound? P norm of f into mod f whole raised to, or 1 minus p into p minus 1. Okay. When it is essentially bounded, f star will be belongs to L infinity, right? Okay. Then what is the rest statement? We need to prove that integral over E f into f star is equal to P norm of f and Q norm of f star is equal to 1. Okay. Okay, so now we are going to prove these two are equal. Okay. So for that, I have to consider integral over E f into f star. So what is f star? And we are going to prove this for the case p equal to 1. Okay. When p equal to 1, okay, what is f star? F star is equal to this formula, right? P norm of f into 1 minus p signum of function f mod f raised to p minus 1. When p equal to 1, this will become 0, this will become 0. So these two terms will be 1. Therefore, f star will be equal to signum of f, right? Okay. F star will be equal to signum of f. Then you consider integral over E f into f star. That is equal to integral over E. We want to prove this equal to P norm of f. Okay. F into signum of f. A function into signum of f will be always equal to f into signum of f. Signum of f will be always equal to mod f almost everywhere on E. Okay, we know this. Then multiply ചെയ്താൽ എന്തായാലും mod f ആയിരിക്കും നമുക്ക് കിട്ടുക almost everywhere. So this can be written integral over E mod f. Okay, what is integral over E mod f? This is equal to, by definition, 1 norm of f. Okay, so you proved this for the case of p equal to 1. Now we want to prove norm of q norm of f star equal to 1. What is q norm of f star? Q norm of f star is equal to, by definition, q norm means subnorm, essential subnorm, right? So what is f star for the case p equal to 1? Signum of f. So this is signum of f. Essential supremum of, this is essential supremum of signum of f. What is the essential supremum of the function signum of f? It has only values 1 and minus 1. Then its modulus will be less than or equal to 1. So essential supremum will be equal to 1, right? So you proved q norm of f star is equal to 1. So we proved that theorem for the case of p equal to 1. Okay. Now case 2, 1 less than p less than infinity. Okay. So assume f comma g are non-zero. If they are 0, then we have nothing to prove. So f and g are non-zero functions and f belongs to LP and g belongs to LQ. Okay. Where q will be the conjugate number of p. Okay. Now also assume that without loss of generality, we assume p norm of f is equal to 1 and q norm of g equal to 1. Why we are choosing such type of functions f and g? എല്ലാ ഫംഗ്ഷൻസിൻ്റെയും പി നോമും ക്യൂ നോമും കറസ്പോണ്ടിങ് ക്യൂ നോമും 1 ആവണമെന്ന് നിർബന്ധമില്ലല്ലോ. ദർ ഇസ് നോ നെസസിറ്റി ഫോർ ദാറ്റ്. So suppose we have functions which are their norms are not equal to 1, then this result will be true for the function. You can consider, I can write here, if p norm of f is not equal to 1 and q norm of g is not equal to 1, take another function, some f1 is equal to, f1 is another function, f1 is equal to f divided by p norm of 1. Okay, then what will be p norm of f1? That is p norm of f1. f1 is f divided by p norm of f. Remember, p norm of f is a well defined real number. ഇവിടെ നോം അപ്ലൈ ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് എപ്പോഴും കിട്ടുന്ന ഒരു റിയൽ നമ്പർ ആയിരിക്കും. പിന്നെ അവിടെ അത് ഫംഗ്ഷൻ അല്ല. ഓക്കെ, സോ ദിസ് ക്യാൻ ബി ടേക്കൺ ഔട്ട് സൈഡ് ബിക്കോസ് ഇറ്റ് ഇസ് എ റിയൽ നമ്പർ. സോ 1 divided by p norm of f can be taken outside. Then inside that this p norm we have f only. So these two are same, so that can be cancelled, so we get 1. So when p norm of f is not equal to 1, we can apply this theorem for f1. Okay, so without loss of generality, this f1 will be taken as f. Similarly, in the case if this q norm of g is not equal to 1, you take g1 is equal to g divided by q norm of g. Then what will be q norm of g1? The same case we get q norm of g1. g1 is g divided by q norm of g. So 1 by q norm of g is taken outside because it is a real number, then instead of q norm we get g only. It can be cancelled, we get 1. Okay, so without loss of generality we assume p norm of f and q norm of g equal to 1. Otherwise we can consider this for f1 and g1. Okay, since f belongs to LP means mod f raised to p is integrable, right? Mod f raised to p integrable over on E. Okay, and since g belongs to LQ implies mod g raised to q integrable on E. Okay, then mod f raised to p and mod g raised to q will be two real numbers, right? They are integrable means they exist, their value will be finite. So that we can apply the Young's inequality. By Young's inequality we will have modulus of a into b will be less than or equal to mod or equal to, we get mod a raised to p divided by p plus mod g raised to q divided by q almost everywhere on E. Okay, almost everywhere on E. Now we want to prove that our Holder's inequality for this case. Now we integrate these functions both sides, so we get integral over E mod fg will be less than or equal to 1 by p into integral over E mod f raised to p plus 1 by q into integral over E mod g raised to q. Okay, so what is integral over E mod f raised to p? We have assumed that p norm of f is equal to 1. What is p norm of f equal to 1? Q norm of g equal to 1. These two equations together implies integral over E. P norm equal to 1 means integral over E mod f raised to p whole raised to 1 by p equal to 1. So whole raised to 1 by p equal to 1 means if you take the pth power both sides, we get this raised to p equal to 1 raised to p. We know 1 raised to p equal to 1. So we get integral over E mod f raised to p will be equal to 1. Right? So in a similar way, when q norm of g equal to 1, you get integral over E mod g raised to q whole raised to 1 by q equal to 1. When you take the qth power both sides, we get integral over E mod g raised to q will be equal to 1. So these two will be equal to 1. So this will be equal to 1, this will be equal to 1. So we get 1 by p plus 1 by q. And we know q will be the conjugate of p. So whenever q is a conjugate of p, 1 by p plus 1 by q will be must be equal to 1. Right? So we get integral over E mod f into g will be equal to 1, less than or equal to 1. Okay. So that this one can be written 1 into 1, or in particular I can write p norm of f into q norm of g. So for this case we get the Holder's inequality integral over E mod fg is less than or equal to p norm of f into q norm of g. Okay. So that we proved the Holder's inequality for the case p greater than 1 or less than infinity. Okay, now we want to prove this statement. Moreover, for f not equal to 0, we need to define f star and integral over E f into f star is equal to p norm and q norm of f star equal to 1. This we need to prove now. So that now consider f into f star. So by definition it is f into f star is defined by p norm of f raised to 1 minus p signum of function f into mod f raised to p minus 1. So which will be is equal to, what will happen? This will be p norm of f raised to 1 minus p f into signum of f, that will be is equal to mod f, right? Then mod f raised to p minus 1. That is equal to p norm of 1 minus p into mod f raised to p minus 1, that can be written mod f raised to p minus 1 plus 1, that will be p. Okay, this is almost everywhere on E because signum of function to f into signum of function will be equal to mod f almost everywhere on E. Okay, so when we get f into f star is equal to this, then what will be integral over E f into f star? We need to prove integral over by theorem we need to prove integral over E f into f star is equal to p norm of f. So you consider integral over E f into f star. That will be is equal to integral over E this statement, right? Integral over E p norm of 1 minus f into 1 minus p raised to 1 by p mod f raised to p. So that will be equal to, this one can be taken outside. So p norm of f raised to 1 minus p will be a real number that can be taken outside. So inside that integral over E mod f raised to p. So this will be the remaining part. So which is equal to, what is this? P norm of f raised to 1 minus p into, what is this? We have p norm of f is equal to, by definition, integral over E mod f raised to p whole raised to 1 by p. Okay, so p norm of f raised to p will be, if you take the pth power both sides, we get this raised to p equal to integral over E mod f raised to p. Again, p, when you take the pth power of this one, 1 by p will be cancelled, so we get this. So integral over E mod f raised to p can be written p norm of f raised to p. So here we can replace this by p norm of f raised to p. So these both are p norm of f raised to 1 minus p and p. So which is equal to p norm of f raised to 1, that is p norm of f. Okay, then what is q norm of f star? Then we need to prove q norm of f star equal to 1. What is q norm of f star? Q norm of f star is equal to, so this is equal to, by definition, integral over E mod f star. F star means norm of p norm of f raised to 1 minus p signum of function f into mod f raised to p minus 1. This is mod f. Okay, suppose if you consider f star as m, f, q norm of f is equal to integral over E mod f raised to q raised to 1 by q. Okay, instead of f we write f star. So this can be written, yeah, this can be written p norm of f raised to 1 minus p, okay, integral over E modulus of signum of function f into modulus of, what do we have, mod f, actually this raised to q down, mod f raised to p minus 1 raised to q, okay, whole raised to 1 by p, 1 by q. Okay, so what is p norm of f? We assumed that p norm of f is equal to 1, so this will be 1. What is modulus of signum of function? Signum of function takes the values 1 and minus 1 only, so their modulus will be 1. So this will be 1 and this will be 1. So the rest of them, integral over E mod f raised to p minus 1 into q. What is p minus 1 into q? We already proved that p minus 1 into q is nothing but p. Okay, because 1 by p plus 1 by q equal to 1, you can solve p minus 1 into q equal to p. So p minus 1 into q will be taken as p. So this is mod f raised to, so this will be p minus 1 into q will be q, okay, whole raised to, this will be 1, this will be 1, then whole raised to 1 by q. And what is this? Integral over E mod f raised to q whole raised to q will be, q into p minus 1 is p, q into p minus 1 is p whole raised to 1 by q, and we have assumed that p norm of f is equal to 1, so this will be 1 raised to 1 by q will be 1, so you get q norm of f star is equal to 1. So we proved the theorem or the Holder's inequality, and we proved that conjugate q norm of the conjugate f star is also equal to 1. Okay, next we prove the Minkowski's inequality, which is actually the triangle inequality of p norms. In order to prove capital LP is a normed linear space. Okay, so Minkowski's inequality says if E is a measurable set and for 1 less than or equal to p less than or equal to infinity, if f and g are LP of E, then their sum f plus g belongs to LP of E. And we have this inequality, this is called Minkowski's inequality, very important one. P norm of f plus g less than or equal to p norm of f plus p norm of g. Okay, we already proved that capital LP is a vector space, right? Is a vector space over R. So when F belongs to LP and G belongs to LP, then their sum F plus G must be belongs to LP. So F plus G will be integrable. Okay. Then we need to prove this inequality. Here also we prove this by cases. Case 1, if P equal to 1. When P equal to 1, then we have Q will be equal to infinity, right? So we need to prove this one. What will be that? 1 norm of F plus G less than or equal to 1 norm of F plus 1 norm of G. Okay. So you consider P norm of F plus G. So P norm means here it is 1 norm. So F plus G 1 norm. That is by definition integral over E mod F plus G. Raised to 1 whole raised to 1 by 1. That is trivial. Okay. And this can be written modulus of F plus G will be less than or equal to integral over E mod F plus mod G. Again by the property of Lebesgue integral, this will be less than or equal to integral over E mod F plus integral over E mod G. And this is nothing but 1 norm of F plus this is nothing but 1 norm of G. Okay. So you get 1 norm of F plus G is less than or equal to 1 norm of F plus 1 norm of G. So we proved for the case P equal to 1. Okay. Now for case 2, we assume 1 less than, P less than. Now what is the case for P equal to infinity? For the case P equal to infinity, what will happen? We need to prove that P norm of, instead of P norm, I have to write the subnorm, right? So we want, you consider what will be the infinity norm of F plus G. That is by definition essential supremum of the function F plus G. We already proved that essential supremum of F plus G is less than or equal to essential supremum of F plus essential supremum of G, and this is nothing but subnorm of F and this is nothing but subnorm of G. So for this case also we proved. Now we will prove the third case, that is 1 less than P less than infinity, Minkowski's inequality hold. For the third case, for 1 less than P less than infinity. Okay. So consider, we consider P norm of F plus G. So P norm of F plus G can be written, before that I am going to use the Holder's inequality. So what is Holder's inequality? When we have two functions, or when we have a function F non-zero function, by Holder's inequality, if F is non-zero, we will have F star, such that integral over E F into F star will be equal to P norm of F. We have this result. Now I am going to use this Holder's inequality, using the statement of Holder's inequality for the function F plus G. Since F and G are non-zero function, we have F plus G is a non-zero function. So there will exist a conjugate F plus G star. For the F plus G star, we will have this result, right? So I am going to use that one. Okay. So by Holder's inequality, by Holder's statement for F plus G not equal to 0 and its conjugate F plus G star, we have integral over E F plus G into F plus G conjugate will be equal to P norm of F. Here instead of F I have to write F plus G. This is, we have the statement. So I can write P norm of F plus G, this will be equal to integral over E, I can multiply this one, F into F plus G star plus G into F plus G star. So which will be equal to, which will be equal to integral of summation will be less than or equal to sum of integral, that is integral over E F into F plus G star plus integral over E G into F plus G star. Okay. So this will be less than or equal to, again I am going to use the Holder's inequality. By Holder's inequality, we have integral over E mod fg, right? Or fg will be less than or equal to, mod fg is less than or equal to p norm of f into q norm of g. This is, we have the Holder's inequality. So I am going to use this Holder's inequality for the function f and f plus g star. Okay, f plus g star. When f belongs to LP, its corresponding conjugate will be belongs to LQ. Okay, so when we know f and g are belongs to, we have f and g are the functions belongs to LP. So their sum f plus g belongs to LP. Then their conjugate f plus g star will be belongs to LQ. Okay, so q norm of f plus g star will define, which implies we can consider q norm of f plus g star. We can't consider q norm of f plus g. We need only consider, we cannot only consider q norm of f plus g star. Okay, is defined, well defined. So instead of g, I am going to consider f plus g star. Instead of f itself. So this inequality will become less than or equal to, you are using Holder's inequality for this one and again Holder's inequality for this one. So by Holder's inequality, this will be less than or equal to p norm of f into q norm of g, where g is f plus g star, plus here also p norm of g into q norm of this second one, that is f plus g star. Okay, so this will be is equal to, what will happen, this one is a common term that can be taken outside. So, or p norm of f plus p norm of g itself. Why? By Holder's inequality, we already proved that when you find out f star, that f star belongs to LQ and their product f into f star, integral over E f into f star is equal to p norm of f, and we have the one more statement, one more equation, f star q norm of f star is equal to 1 by Holder's inequality. So here also q norm of f star will be well defined, and that value is, and that is equal to 1 also. So this will be equal to 1 and this will be equal to 1. So you get p norm of f plus g will be less than or equal to p norm of f plus p norm of g. So we proved the Minkowski's inequality for all these cases. For case 1 p equal to 1, for the case 2 p equal to infinity, and in between 1 and infinity we already proved by Holder's inequality. So we have Minkowski's inequality. By Minkowski's inequality, for the elements in LP, it's also hold for triangle inequality. Therefore, I can say that capital LP of E is also a normed linear space. Normed linear space over R.